In this video, we're going to talk about the last operation on matrices that we're going to do in this class. It's called matrix multiplication. So here we're multiplying two matrices. It happens to be the most complicated of our operations that we're going to look at. And unfortunately, it's probably not what you're thinking it should be. So we can't just take matrices of the same size and multiply corresponding entries like we did with addition and subtraction. This is a type of matrix multiplication. It's called sure multiplication. But for applications, what we actually require is something a bit more complex. So to introduce that, we're going to try to break down the idea. So first we look at how do we multiply a row matrix by a column matrix, because this is what we're going to need in order to do our matrix multiplication. So we have matrix A here, that's a row matrix, and it happens to be, so it has one row and n entries, so n columns, so it's a 1 by n matrix. And then we have matrix B over here that has n entries as well, so it's an n by 1 matrix. So we define I'm calling it row column multiplication. So A times B here. So what you do is you take the first entry in each of these matrices and you multiply them together. And then you add the second entry in each of these matrices, multiplied together, add it, multiplied, and then add together, all the way until the last ones. And you add up all those different things. Okay, so it actually is helpful. It's hard to do on here. It's helpful if you use your finger and you slide across this matrix and down this matrix at the same time, so at the same speed. So note, okay, the sizes, or maybe I shouldn't say sizes, let's say the number of entries in each of these matrices is the same. Okay, so we need them to match up so we can pair them off and multiply them together. So let's do an example. So if these are our two matrices, so A and B, then A times B is going to be 2 times 1 plus 1 times 5 plus 4 times negative 1. And what we're going to get is a 1 by 1 matrix. Okay, so it's just a number. In some places, if you read alternate textbooks, they might call this a dot product. Okay, so that is another name for this. So if we multiply these together, so it's 2 plus 5 minus 4, so I'm going to get the number 3. Okay, so you always get a number when you take a row matrix and you multiply it by a column matrix. So when we do matrix multiplication for bigger matrices, so here we have for A, matrix A is size m by n, and matrix B is size p by q. What we're going to do is we're going to use this row column multiplication to compute each entry of our new product matrix. Okay, so we're going to take each row, so let's say we take the ith row of A, and we're going to get the entry in the ith row and the jth column of our product, we're going to take row I of A and multiply it by column J of B. So I'm going to try and draw you a picture here. Okay, so let's say that this is A, and it's m by n, and then we have some matrix B, that's p by q, and we're going to get some product, okay, AB, assuming it exists. Okay, so let's say that I take something in row I, column J here. So to compute this entry, what I'm going to do is take row I of A and column J of B, and we're going to multiply this row by this column, The number we get is going to be that entry there. So there's a few things that we might notice right away. First of all, like I said, when you take a row and you multiply by a column, the number of entries has to match up. So we needed that there was n columns in A and n rows in B. So in order to be able to do this, I need the number of columns to match the number of rows in matrix B. Okay, so this is how we know when the product is defined. So AB is defined only when n is equal to p. Okay, so that's the number of columns in A is equal to the number of rows in B. And if you write, so a useful way to think about this, if you write their sizes next to each other, okay, so this is why I always write their sizes. The ones that are closest together, okay, they need to be the same. So if they are the same, so if n does equal p, so the multiplication is defined, then AB, the product, will have size m by q. Okay, so those are the outer ones. So that's going to be our new size for our matrix. So let's do some examples to try and get the hang of this. So we want to make sure that the multiplication is defined. So let's think about the sizes of each of these first. So if this is matrix A, okay, and that one's matrix B, the first one is a 1 by 3 matrix, and the second one is a 3 by 2 matrix. Okay, so notice that those are the same. So that means that we can do the multiplication. And what we're going to get is a 1 by 2 matrix. Okay, so we sort of know what the size is going to look like. So what we're going to want to do is take this row and multiply by this column. And that's going to give us the first entry here. So that's going to be -1 times 6 plus 2 times 4 plus -3 times 0. Okay. And now we're going to do the same thing. So we take this row, so there's only one row, and we multiply it by the second column, and that's going to give us the entry in row 1, column 2. So this is going to be -1 times -8 plus 2 times 9 plus -3 times 11. So now we just want to simplify. So -6 plus 8 plus 0, and then 8 plus 18 minus 33. So we're going to get a 2 and then a -7 in the other spot. And notice that our matrix is in fact a 1 by 2. Okay, let's try another one. Now notice this is the same as A, but in the opposite order. So I wonder if that's going to make a difference. So again, let's first think of the size. So the first one we already said was a 3 by 2, and the A matrix, so now what I'm doing is B times A. The A matrix is a 1 by 3, and notice that these inner sizes, they do not match. So what that means is that this operation is not defined. Okay, so if we were to try to take a row here and times by a column here, notice that there is not enough entries, right? We need an entry here in order for it to match. Okay, so because they don't match, our operation's not defined. So the order that we wrote them makes a difference, right? One of them is defined and one of them is not defined. We can't even do it. So let's try another one. Here, so this is A, this is B. Again, we have a 3 by 2 matrix, and we're multiplying by a 2 by 2 matrix. So those are the same. Okay, so that means that we can multiply, and we're going to get a 3 by 2 matrix as a result. Okay, so we take each row and we multiply by each column. So I'm going to take, so we take row 1, multiplied by column 1. That's going to give us our entry in row 1, column 1. So it's going to be 2 times 1 plus 1 times 4 for that entry. Now we need to take row 1 again. Okay, but this time we're going to multiply it with column 2. So that's going to give us the entry in row 1, column 2. So it's going to be 2 times negative 3 plus 1 times negative 1. Okay, now I need to do the exact same thing with the 2 other rows. Okay, so now I take row 2 and I multiply it by column 1, and that gives me the entry here. So it's going to be 0 times 1 plus 1 times 4. Okay. So now I want to do that row again, but now with the column 2 is going to give me this entry here. So it's 0 times negative 3 plus 1 times negative 1. And now, maybe I'll try and do this with color. So now I take this row and this column. Okay, that's going to give me the entry here. So that's 1 times 1 plus 3 times 4. And then I want to take that row again with this column over here, and that's going to give me row 3, column 2. So it's going to be 1 times negative 3 plus 3 times negative 1. And now if I simplify each of these, so it's 2 plus 4, that's 6. Negative 6 plus negative 1 is negative 7. 0 plus 1, or plus 4, sorry, is 4. 0 plus negative 1 is negative 1. 1 plus 12 is 13. And negative 3 plus negative 3 is negative 6. And notice that it's a 3 by 2. Okay, so that's how we compute a matrix product. Let's do a couple of more. Now again, notice that these two examples are the same, okay, but in the opposite order. So above, we saw that one of them isn't defined, but here, in fact, they're both defined because both the matrices are 2 by 2. Okay, so that means that they're all 2s. Okay, so the inside ones are going to match on both sides. So if they're both defined, maybe we'll get the same answer. So let's try it out. Okay, so I'm going to get a 2 by 2 matrix. So we take row 1, column 1. That gives us our first entry. So negative 1 times 1 plus 0 times 3. And then we do row 1, column 2. And that gives us our entry in row 1, column 2. So negative 1 times 4 plus 0 times negative 1. Okay, now I have to do the same thing with row 2. So it's 2 times 1 plus negative 1 times 3. And then last, row 2 and column 2. So it's going to be 2 times 4 plus negative 1 times negative 1. So here we're going to get negative 1 plus 0 is negative 1. Negative 4 plus 0 is negative 4. 2 minus 3 is negative 1. 8 plus 1 is 9. Okay, so that's our 2 by 2 matrix. Okay, I'm going to do this last one without colors, so hopefully that's okay. Hopefully we're getting the hang of it. So row 1, column 1, it's going to be 1 times minus 1 plus 4 times 2. And then I'm going to have 1 times 0 plus 4 times minus 1. Then I have 3 times minus 1 plus minus 1 times 2. And then 3 times 0 plus negative 1 times negative 1. So if we simplify here, I have negative 1 plus 8 is 7. 0 plus negative 4 is negative 4. Negative 3 plus negative 2 is negative 5. 0 plus 1 is 1. Okay, so now notice, even though our answers were both, they both exist, okay, they're still not the same. So these two matrices are different, okay, they're not equal. So that's my note that I want to say. So you want to be really careful. This is something that you probably haven't seen before, because multiplication or real numbers behave nicely for us. Okay, but in general, for matrix multiplication, A times B is not equal to B times A. Sometimes it might turn out that they are, okay, but in general, it's not the case. Okay, so even when both operations are defined. So you want to be careful that the order that you write them matters. Okay, so you need to keep that in mind.